we will now look at the pseudocode, and we can start with simplex. Okay, so the variables in the pseudocode correspond to the variables used in the description of simplex, such as x, a, b, and c. Okay, so simplex is described by this struct, and this struct has really non-C syntax. You cannot write it like this. But it's not intended to be C code. Instead, it's intended to be as clear as possible in as fewest lines as possible. Okay, so the number of constraints, the number of decision variables, and then this array var, it says which variable is at a certain position. So the first n of these are the current non-basic variables, and the rest are the current basic variables, which means that we know which one is which for the moment. Okay, so when we move, when we swap non-basic and the basic, we will move them here. Okay, so the matrix, it needs one more extra column actually, and that's because that's needed when Origo is not in the feasible solution. Then we need another variable and solve another system. So we reserve one extra at the beginning. Okay, and this that the extra is also due to the same reason. Okay, so the others should be self-explanatory. So let's go into simplex, and we have it here, there. And what it does is to start with calling x simplex, which has a variable that is 0 the first time, meaning that we are calling simplex from outside. And if h is 1, it means we call simplex recursively. Actually, there is only one level of recursion, and that happens when there is a negative b. So it's h is always 0 or 1. So don't think of it as a recursive function, just as we solve a different system first, if there was a negative b. Okay, so what happens? First, we try to initialize this struct, and if that didn't work out, then there was no solution, so we return not the number. And what we do then is to find a non-basic variable that we should swap into and become a basic variable. Okay, so we want to find a column, and we do that by looking for a variable with a coefficient that is greater than 0. Here, select non-basic. So we check all these, and if it's greater than epsilon, epsilon can, for instance, be 10 raised to the power of -6 or -9. We should not use exactly 0, but some epsilon, due to numerical errors that can happen. Okay, why they can happen will be explained later in the course. So then when we find the positive coefficient, we take that one. If there was none, then we return -1 instead. Okay, oops. So if we found one, I mean, we set the column and check if it was greater than 0 or equal to 0. Then we look for the row, and that is the basic variable which is most constrained by this non-basic variable. Okay, so we want to find that row, and then that row and column, I mean the variables for that row and column, will switch roles. So the non-basic becomes basic and the basic becomes non-basic. And if we didn't find any, that means there is no way, I mean the system is unbounded, since no basic variable was limited by this non-basic, and so we return infinity. Otherwise, we do something called pivot, which means swapping the basic and the non-basic. Okay, so let's look at it. This is where most of the time is spent. I really recommend doing this by hand first. Well, you don't have to, but it's probably a good idea. Okay. I will not explain every line here, but it does exactly what I described when we swapped place between the non-basic and the basic. So it's just the tedious calculations, but they need to be done. Okay, so when we have done that, we continue and look for a new, I mean, what we have done now is to move to a certain vertex, to a neighbor vertex. And then we continue, and if we can, well, we continue until we cannot find anything that is better, and then we quit. What we do then is to check if h is 0 or 1, and depending on which it is, we will update the solution vector slightly differently. If you do this by hand once, you will see what this means. Okay, so well, we can look slightly what this means. So this is the normal simplex, and we go through all the variables, and if that variable is a non-basic variable, then it's set to 0. Otherwise, we go through the basic and set them to the corresponding b value. Okay, and well, it's similar but slightly differently implemented if we use if we come here recursively. Okay, so we should also look at this code, but I will not talk very much about it. But this is when we create the initial system. So simplex calls initial here. And the first thing we do is to call init. And init will create this simplex struct. So here is init. And what this line means is that we should create a struct of this approximately this type and assign each parameter to each attribute. You may think that the variable names are quite short, and I would certainly agree, but it's in my view much easier to read short. I mean, if you just have short variable names without any explanation what they mean, then of course it's a little bit problematic. But if you have mathematical theory but about what m, n, a, b, c, etc. mean, then there is really no point in having long so-called descriptive variable names that just take time to read. No one solves equations using 20 character long variable names, so to speak. We prefer X. Okay, so when you have learned the basics of this, it will be much more convenient to have M and N, etc. So we initialize it and say that each variable from the beginning is in its original position. And here we look for the smallest b. So in this case we will, doing that we will discover if there is a negative b. We take the smallest one, and this is called from initial, so we return here. And if now k is the smallest b, index to b, that is the smallest, and if it was positive or 0, then the initial solution, the origo is part of the region, feasible region, so we will just return 1 and solve the simplex. Otherwise we will need to do some preparations to solve a different simplex, which I will not explain now because it's much better if you have solved the first version, without this problem. But essentially we create a new problem and solve that using simplex to find an initial point where we can start the simplex algorithm for the problem that we had. Okay, this is quite long, but well, that's needed. Okay, let's look at branch and bound instead. Okay, and I will just explain the basics. We start with creating this initial node. Auto is should not be considered to be C auto keyword, which is completely meaningless, but instead for C++, so we should select the type depending on what is returned from here. So we get a node from here, and then we have a set of such nodes. That's the nodes that we will explore in the future. And the best solution so far is not so good for maximization. Okay, we get the first solution from simplex with relaxation, and if it's an integer solution or it's not finite, then we don't have to solve anything more and we return it. If it was an integer solution, then we copy what we found from simplex into our variable array. In the pseudocode, as you can see, I avoid loops when possible, so that we can say copy this array into that array. That's easier than having a for loop. Okay, and then if we didn't return, we will branch, and then we loop until this set is empty. So we take something from the set and create two successor nodes. So we use the floor and the minus seal for this to set up the new linear inequalities. Okay, and then we can delete the parent. Okay, so what is interesting here? Integer p, that goes through all the variables, and it's not very strange. It's simply like this, and it's not as easy as you thought, I guess, because what we need to do is to round this to an integer and then check if it's close enough to being an integer. So it's not sufficient just to check if it is an integer. Okay. I mean, with using some other version of some other code, but we need to check if it's good enough that it looks like an integer. Okay, is finite. That's you don't have to implement, but I coded it like this in the pseudocode since that's more for documentation. There is a C library function called isFinite which does exactly this. Okay, so then let's look at creating a successor node. So first we check if we should extend the system or not. And if we should, then we solve simplex with it. And okay, if it's a finite solution, and then we are interested. If it's also an integer solution, then we can bound by throwing away pointless nodes in the tree, in the search tree, by bound. Okay, bound, it simply says save the best and remove everything that is bad. And otherwise we check if we should branch and then add this to the set H. Okay, I will not go through every detail here, but this is a good start. This extend should get all the constraints from the parent node. And these are really not complicated things if you do them by hand first with pen and paper. So that's a good idea. I mean, that's just an option to do that. You don't have to, of course. Okay, so that's it.